Should I start? Oh, okay. All right. Yeah, I'm all wired up. Yeah, okay. I'll be light entertainment. Oh, we'll see. Okay. All right. Thanks. Yeah. Yes, that's my name. I'm from Chicago, and the best way to reach me if you have any questions, either about the lectures or something else, send me an email. Yeah. So originally, as Marian said, I was planning on doing some more specialized lecture on collider physics. But then I saw that I'm probably the only lecturer, focusing more on the theoretical aspects of particle physics. So I decided to give a more general lecture. Basically, I'm going to so just a very rough plan. I'm going to go over the standard model. Okay, so hopefully you have all seen the standard model in some form, right? Okay. we'll see, and hopefully I'm. I know. So I'm going to start from compactifying type 2B. Anyway, so hopefully I'm presenting in a way that is slightly different from what you learned in your particle physics core class. Okay, so this is really setting the stage of outlining some of the problems or questions, open questions about the standard model, and then we move on to the next topic, which is what is basically the current thinking about the beyond standard model, new physics. And well, depends on how fast we go. I guess this will take quite a bit of time already. And in the end, I'll talk a little bit about how to look for those new physics at the colliders. And depends on how fast we go. We can even talk about other things too. But these are the basic things. Yeah. Okay. So, and I also realized that probably most of you don't really work on particle physics. I'm not trying to convince you to. I'm not trying to convince you to change your direction, but at least I wanted to show you what are the what are some of the interesting questions in this field. Okay. Standard model. Okay. So we just the very basic things. You all know there are three interactions. Fundamental interactions, the strong, weak, and ENM, and there are quarks and leptons, and yeah, okay. So, but let me just briefly write the representations for you. It's just so there are Q's. Just to set the notation. There are QL. Which, okay, let me write it. U, D, L, E, R, H. Okay, So this is just the notation. These are right-handed quarks, and this is left-handed quarks. So it's collectively denoting UL and DL. Okay, so left-handed and right-handed. So imagine for the moment nobody has mass. Okay, so that the chirality is yeah. So this is very well defined. So SU3C, that's the gauge symmetry for strong interaction. SU2L and U1Y. Okay, so okay. So yeah, so this is a. I hope this is very well known. Okay, and 2, 1, 1, 2, 1, 2. Okay, and so this is the left-hand doublet, and this is a left-hand neutrino and the left-handed electron, and this is the left-handed right-handed electron. Okay, right-handed lepton. Okay, and the U1Y charges are 1,6 for the doublet, and so these are the quantum numbers for the relevant for the gauge interactions. Okay. Any questions about this? So it's hope this is good. Okay. So these things, although I write it as one set of fermions, but there are 3 generations. Okay. So there are 3 generations, and the quarks and leptons. Okay. Okay. And from that on, I assume you know how to write a Lagrangian, the gauge invariant Lagrangian. Is it okay? Do I need to write it? Well, we'll write bits and pieces of it as we go through more of the dynamics of standard model. Okay. All right. So, in principle, you can just go from here and write the most general Lagrangian and calculate things and experimental data. So that Lagrangian will contain, I think, roughly 20 parameters, and you can fit to the experiment with those parameters, and you can do your calculation, and it all works. Okay. All right. So that's the end of our lecture. Okay. All right. So in order to, but this is not what we do. We don't, as a particle physicist, we don't really, well, we do this, but it's not like every time you wanted to do something, start from the beginning. So it's very useful. The dynamics in particle physics are very useful. Be thought about and governed by a lot of symmetries. Okay. I don't mean these symmetries. Okay. These are gauge invariants. I don't mean these. I mean global symmetries. And so let's spend some time talking about it. And also, the thinking about global symmetries and symmetry breaking is also very useful for BSM. That's why the standard model part is a nice warm up to those things. Okay. So let's see. This is what I really wanted to spend some time talking about: accidental symmetries. They are approximate. Okay. So first of all, everybody knows why they are called accidental. Why are they called accidental? What symmetry is accidental? in this sense, in particular, I mean that these are the symmetries of low energy effective Lagrangian if I only keep finite number of terms. Okay? Means that we don't expect, or we don't necessarily expect these to be exact symmetries. Okay? But the symmetry breaking effect at the low energy effective Lagrangian is small. Okay? So both, you will see that both the fact that this is accidental and that this approximate are very important. Okay? Yeah.
Do you consider all global symmetries to be accidental?
Well, again, you know, so if you write a renormalizable Lagrangian, right? You see there's going to, because the simplicity of the Lagrangian, there are going to be accidental symmetries. Okay. Now, a priori, you know, from the low energy effective field theory point of view, or from experimentalist point of view, you know, you shouldn't expect any of them to be exact, right? They will be violated by small parameters you haven't measured yet. Right. So that's the attitude. Okay. Of course, if you are convinced that type 2b is the order and you can verify, then yeah, everything is, you know which one is exact, which one is broken. Okay. All right. So let's get on with it. So these are very important concepts. It's simple but very important. Okay. So this is a. So let's first do B and L. Okay. Baryon number and the lepton number. These are accidental symmetries of standard model Lagrangian. Okay, just so these are defined as the following, I think. So these are quark. We'll refine a little bit of this later, but at this level, just accept as it is. Okay, so these are the matter fields. Quarks are charged 1/3 under baryon number, and leptons are charged under 0, and this is 0, and the Higgs do not charge. Okay, so these are the accidental symmetries. Okay, broken by electroweak anomalies. That's a subtle, somewhat more subtle point. At least, so let's put the anomaly aside. These are this is accidental symmetries. Okay. Now, as I said, these are approximate, right? Therefore, in general, as an effective field theory, you should also write down operators that can potentially break these symmetry. Okay. So one such a possibility, B and L breaking operator, is, for example, okay, it's a higher dimensional operator. As I said, these are the symmetries of a renormalizable standard model Lagrangian. So one of them you can write is this. I'm not being very careful with the Lorentz structures and the color indices contractions, but it looks like this. Okay. Okay. So 3 quark, 1 lepton. Okay. Now, what's the observable effect of this operator? If this one is large, we will not be here. Proton will decay. Okay, and so this leads to proton decay. Okay. And the limit on proton decay lifetime. So by the way, this is what they do. You get a swimming pool, and you will never wait for such a long time, right? Okay. the way to do this, you get a swimming pool, and you hope that a lot of them, even though the one decay probability for each one of them is very small, but since you have a lot of them, you may be able to see one of those decay. Okay, so and the lifetime is about this. Okay, so you can roughly do a calculation from this. Okay, on the lifetime of proton. So the way to do it is inverse lifetime is what we call the width of proton. Oh, what's the unit of width? GeV, right? Mass. And so it has to be proportional to this operator square. Right. So 1 over m to the 4th. And that this doesn't look like the right unit. So have to be something upstairs has to make up the unit. So what's upstairs? The only other dimension for quantity is proton mass. Okay, so m proton. Okay, that's roughly the lifetime given this operator. And there are some pi's and so on. Well, since this is a formal theory, Tarsi school, we work in the unit, the pi equal to 1. Okay, so. All right. Anyway, so this, if you plug in, you do a slightly better calculation, and this is roughly speaking 10 to the 15 GeV. Okay. So this is what kills the first generation grand unification series. By the way, they have this operator, but they unify around the 10 to the 14 GeV scale. So this will give you the proton lifetime too short. But yeah, so greater than that, roughly speaking, is still allowed. Okay, so we may come back to that later, but right now let's just stay with where it is. The next set of symmetry is that there are lots of fields, right? There are, what I said is there are 3 generations of quark and leptons. Okay, so these are called the flavors. Right. I don't know why it's called the flavors, but it is called the flavor. Okay. And just like this is called the color, and something is flavor. And okay, there's something called the odor too. I think called the smell too, by Bob Holden, I think. Anyway, yeah, it doesn't stick. So all right, flavor. Okay, but so we expect there will be flavor symmetries. Okay, so let's talk about flavor symmetries. So D and L is a symmetry that you expect, modulo anomaly, you expect to be preserved to a very high degree. Okay, this is just saying that this operator is very, very small. The contribution is completely irrelevant for most of the experiment you do. You need to build a very sensitive experiment to be able to to detect that. Okay, flavor symmetries. So for the moment, so I suppose you know that the standard model, we can go through it, we'll go through it, but for the moment, let's switch off all the masses. In fact, let's switch off all the coupling between the, right, so let's switch all those Yukawa couplings. Yukawa couplings looks like, by the way, it looks like this, for example. Okay, this is what the upper type quark gets flavor. Gets its mass when Higgs gets a VEV. Okay, so this looks like a quark mass, and in principle there are flavor indices I and J's here, and this is actually a matrix, not a single number. Okay, but for the moment, let's switch all these off. Okay, let's set all these to be 0. Okay. The reason to do that is that you will see, it's very useful to think about the global symmetry. Is that you find a global symmetry and they're broken by a set of parameters. Okay, it's very useful to make that distinction. Right. And so these are sometimes called the spurions of the symmetry. And you do, after that, you do a spurion analysis. You can yeah. Okay. So let's switch off all the quark and the lepton Yukawa couplings. So now then we only have kinetic terms. Okay, we only have kinetic terms. Right. The kinetic term basically looks like this, something like that. Okay, with the flavors indices here, which commute with all the gauge rotations. Okay, so flavor symmetry in quark sector. In quark sector, okay. So how many of them? Okay, all the QLs. There are three different left-handed doublet, right? I can rotate among them, do arbitrary flavor rotations. Okay, so it will still keep this one invariant. Okay, imagine now I have flavor indices here, right? So you just do rotations. This is invariant. So there is a U3Q. Okay, this is the flavor rotation in the left-handed quarks. Same, there are right-handed rotations as well. They are also symmetries for the kinetic term. Okay, these are the flavor symmetries. Okay. Now, at this moment, so these are the symmetries without Yukawa coupling. Now let's switch back on Yukawa couplings. Okay. Now you turn on the spurions. Okay. So the quark Yukawa couplings, there's YU and then there's YD. Okay, up and down Yukawa couplings. Right. So this is a general 3×3 complex matrix. This is a general 3×3 complex matrix. Okay. So how many parameters are there? So this is a This is 18 real, 18 complex, 18 imaginary. Okay. So 18 real. And think about it as this. Okay. So it looks like I have 18 real flavor parameters, 18 faces parameters. Right? No. It turns out the answer is because I haven't used all the degree of freedom to rotate away the faces. Okay, I can do flavor rotations. I can do U3 flavor rotations to get rid of parameters. Because the U3 rotation is a symmetry of a kinetic term. They only change Yukawa couplings. Okay, I can use these to rotate away faces. Is this okay? Okay. So let's count. Okay. So U3 cube has how many parameters? Has 18 faces. It's corresponding to 18 faces. Okay. Anyway, you count yourself. Okay. It's 18 faces and the nine real parameters. Okay. And okay. So it looks like I should be able to get rid of 9 real. Get rid of all the faces. Okay. Except there is one thing. So except these spurions don't break all the symmetries. Okay, it doesn't break these symmetries down to 0. Okay, so in fact it breaks So let's say, where do I say this? Okay. So let me write it in a more Spurian language. Okay. So YU and the YD breaks this U3 cube down to nothing. It's down to the baryon number we talked about. Okay, Yukawa coupling still preserve baryon number. Okay, so one of these phase rotations is just baryon number, and it's a symmetry of the Yukawa couplings. Therefore, Yukawa coupling is invariant under that rotation. Therefore, that rotation cannot remove the phase from Yukawa coupling. Is that okay? Okay. So therefore, really, you can actually remove 17 phases. Okay, you can rotate away 17 phases and 9 real parameters. Okay, now we have a real counting for the number of parameters. Okay, so there are 9 real parameters. Okay, these are these are 6. Well, sorry, these are the 6 masses. Sorry, 6 quark masses, which there are 6 quarks. They all have mass, so there are 6 parameters, and there are 3 mixing angles. We'll talk about that. And there is 1 phase. Okay. So these are the physical parameters, phase flavor parameters in the quark sector of the standard model. Is it phase value CP? Anything else? Yeah. So have you all seen Spurian analysis? Okay. All right. So in a more Spurian-ish language, the way to say this is that suppose you are used to this. All I need to tell you is just that there are 2 Spurians, right? And there are 3 global symmetries. And the Spurians transform under the global symmetry. Okay? They transform. For example, this guy transforms in the 3-3 bar as a 3-3 bar under this global symmetry, and this transform under of a 3-3 bar under this symmetry. Okay? And once I froze this Spurian to its background value, it breaks this global symmetry down to U1B. Okay, so this is in principle, if you are familiar with the Spurian analysis, this is all I need to say. Okay? So if you haven't seen Spurian analysis, learn it. It's very useful. Okay? Yeah, you have to know something. Yeah. Yeah, then have additional bigger symmetries. Yes. Yeah, that's right. Yeah.
Can we think of the quark masses and mixing angles as some kind of like ghost?
These are the background field values. These are not ghost stones. Yeah. So well, you don't really literally think about this as fields. Okay. I guess at least at this level. Okay. These are things has background values. Okay. In the end. So let's do it in slightly more detail. Let's just go down to a bit of detail. How we do it. in the standard model, the flavor factor. Google it yourself. I'll mention those names. You'll hear it. Okay. Yeah. So I'll do it now. So. How should I do this? I'm supposed to use this, right? This. Huh? Okay, I'll use this just to give it a try. So use this. Yeah. Yeah. So phase is what I mean. Phase is just that there is one CP violating parameter. In the CP violation effect is controlled by one parameter. On the other hand, the flavor mixing. You'll see what flavor mixing means. Okay, so the flavor mixing is controlled by three rotation angles. Not the whole real. The sign of quark mass is not physical. So, and but the what I'm not sure what the. Yeah, it's SU3 rotation angles, basically. Yeah. Yeah. Okay. So maybe it will be clear. I will try to well, at least when you see this where those angles show up. It will be slightly better, I guess. Am I supposed to use this again? How do I use this? So in detail, again, so for example, well, I have a up and down Yukawa matrix, and once I give a Higgs of F, and I will rotate the upper quark left and the right, each with a separate matrix. Sorry, let me write it. Okay. Unitary 3x3 matrix. Okay, so these are the let me call this hat, and this this obviously doesn't make sense. Okay, so in such a way that the Yukawa matrix the upper Yukawa matrix. So remember that. Let me just write this. So YU. So I'm starting with a coupling. Looks like this, right? Then the Higgs valve, ULUR. Okay, roughly speaking. Okay, so something like this. And but this is a 3x3 matrix. Okay, with different flavors. And I'm going to diagonalize this matrix. That's these rotations are for. Okay, so the result is that I will get a diagonal matrix, which is basically YU, YD, no, Y charm, Y top. Okay, these are the name of three up quarks. Okay, so this is by diagonalizing it like this, the original Yukawa matrix. So an arbitrary complex 3x3 matrix can be diagonalized by this kind of bi-unitary transformation. Okay. So I'm going to do it, and these are the mass eigenstates, and so these turns into masses. Okay, so M up, charm, and top just turns into Y, up, charm, top times V, basically. Okay. All right. So what is it okay? So I'm going to do this. I'm going to also do this for the down sector. Okay. So this is the down sector. I have these two rotations. So I diagonalize mass matrix. Go to mass eigenstate. Okay, so now in this language, where does the flavor mixing effect go? Right. Of course, now you're rotating the quarks. Of course, this rotation matrix will in general show up in its interactions. Okay. So let's consider different kind of interactions. So in the standard model, weak interaction. So for example, there is a coupling that is dagger. DLW plus minus. Okay, so this is the interaction from the left-handed quarks to W. Okay. Again, I'm assuming that we can go through this, but this is just coming from the SU to L interaction. Okay. And after then you do that rotation. So UL will rotate, DL will rotate, but their rotation in general don't cancel. Okay, so that rotation is not a symmetry of this interaction. Okay, the rotation I just did is not. Okay, and therefore, in terms of mass matrix, mass eigenstate, I will have this sigma U and the two rotation matrix here. Okay, and the W. Okay, so this is our flavor mixing matrix. Okay, so this is the so-called charge current. Charge current interaction because it couples to charge W boson. Okay, and this is sometimes called a Ckm matrix. Okay, it's a 3x3 unitary matrix. Okay. And as we said, that there are three mixing angles in this matrix and one phase, physical parameters. Okay. On the other hand, I can also so standard model also have couplings to neutral gauge bosons to right. So for hypercharge and so on, right. So there are couplings of both left and the right, and it goes like this, and to A mu, okay. And these are the neutral gauge bosons. A mu can be either W3 or B. Okay, so it's the diagonal generator of SU2 or the hypercharge gauge boson. These are all neutral. That's why U don't couple to D, okay, because they have a different electric charge. Okay, U only couples to U. On the other hand, these things, those rotations, are the symmetries of these interactions. Okay. So therefore, even after you go to the mass eigenstate base, it stays the same. Yeah. Let me just write it like that. Okay. So this is another thing. This is called no flavor changing neutral current. No flavor changing neutral current. This is called a well, if this can switch flavor, it's called a flavor changing neutral current. But no flavor changing neutral current in the standard model at the tree level. Okay, I have only proved it to tree level. Okay, and it's in general it's not true, but in tree level it's true. Okay, and yeah, and the tree level is true is very important. It means that any effect, flavor changing neutral current effect will be small, will be loop induced, will be suppressed by additional small couplings and loop factors. Okay, so this is a very important fact. Any questions with the flavor mixings? This picture has been tested a lot. Okay, it works very well. Okay, so of course the way to do this is to observe various things that can change flavor, very flavor changing effect, and because those effects are small, you make a lot of them. Okay, and because these are quarks, and you don't really see quarks. At the low energy, you see mesons, but the mesons also carries the flavor of quarks. So you see the flavor changing effect from the mesons, and these has been tested very well. Let's just say, okay. So basically, one set of tests is basically just test what I said is in this three flavor thing that this is a unitary matrix. Okay, you can one way to phrase the test is that you can test how unitary this matrix is. You try to measure its various elements, and you wanted to see whether it's actually satisfy the relation from a unitary matrix. Sometimes this is called a unitarity triangle measurement. So yeah.
What does it tell you?
Huh? What does it tell me? This means that I'm missing a flavor, for example. Okay, there's something else, right? So I have well, in my notes, I'll try to put my notes online. There's some current figures, but it's yeah. Okay, but let's just talk about one of the things that's received the strongest constraint of flavor. Test the best in the standard model, which is Ckm mixing. Anybody knows what a Ckm is? It's a meson. Okay. By the way, here's a test. Here's a test. I'm not sure whether I can pass myself. Okay. Here's a test whether you say you understand standard model, right? So, and the real test is to open up particle data group. You know, there's something called a particle data group. Yeah. All right. So open up that. See how many pages you can understand. Okay. just roughly. Okay, I'm not asking you to calculate everything, but how many pages you can understand. So I'm sure you will run into
sections or the particle properties?
I don't know. Meson summary tables, left-hand summary tables, just the review section. Yeah, it's good to read the review section. Okay, Ckm mixing. Ckm are the mesons made of by neutral Ckm mixing is what I mean. It is made by down and strange quarks. Okay, so Ckm mixing is ds, roughly speaking, goes to S and D. Okay, this is my initial state. This is my final state. All right. So, and so then a diagram that contributes to Ckm mixing goes like this. Okay, we know that it cannot come from Z and the photon exchange because they preserve flavor. It has to come from the W boson exchanges. Okay, and at one loop. Okay, so these guys are U and the C and the T. Okay, all possible standard model uptype quarks. Okay, U, C, and the T. Okay, and so this operator you can. So Ckm is very light, okay. So you talk about effective field theory of Ckm. You can integrate out the W and the top and so on. Okay. So the effective operator of this mixing is described by the following operator. I guess I'm not working in the pi equal to 1 unit, but this is the loop factor, 16 pi square. The loop factor. Sum over I. Okay, I'll say what so over I, and I equals to U, C, and T, and MUI square MW to the fourth. Okay, MW to the fourth is simple to understand, I hope, because there are these two W propagators. Okay, at a very low energy, each of them give you 1 over MW square, and these are the vertices. These are the vertices that's coming from this. Okay, from the charge current interaction. So it has to basically involve this mixing angle, the matrix element of this guy. Okay, so you can see that this is a VID star VIS square. Okay, matrix element, matrix element, matrix element, matrix element. There are 4 matrix elements, so we need to package it into this, and this is a operator looks like, because it's all left-handed. So this is the operator. Okay. Okay. So, and this operator of course, has been very well tested. It contributes to the fact that the delta MK, so there are 2 neutral K-on state, and this is the off-diagonal matrix element in their mass matrix, basically, and it splits those 2 states, sorry, this is no unit. Okay, it's this. Okay, this has been very well tested. So, but let me also point to you that there is some interesting fact. Okay, there is a quark mass here. Okay, remember, look, there's a quark mass here. Okay, so imagine that I'm in the limit of which is not true in the standard model. In the limit, and the U quark and the C quark and the top quark has the same mass. Okay, suppose I'm in this limit. Okay, and this matrix element is 0. Okay, because this is a, then this becomes exactly V times V dagger square off diagonal limit of diagonal. Right, so I can factor out this MUI and this sums to 0. Okay, so this is easier to understand in terms of symmetry language. Okay, because in this limit there is an enhanced symmetry. There's an enhanced flavor symmetry. Okay, I recovered some of the flavor symmetry that I've broken with Yukawa couplings. Okay, so in fact in this limit I have a additional I have a new flavor symmetry, which is not left, not right, but there's a diagonal subgroup. Okay, left, right, yeah, because I already turned on the quark mass, so it's the SU3 diagonal. Yeah. Yeah.
I guess there seems to be a bit of is there any precision?
So in the end, you have to match this matrix element into a mesonic state. Okay. Yeah, but that's controllable. You can measure that parameter somewhere else, or you can do a lattice calculation to do that. Yes, you do, but that's controllable. Okay, and the fact that this effect is vanishing in this limit. Or said it the other way, the fact that the size of this effect is controlled by the difference in the quark mass. Okay, you can understand. The size of this effect is controlled by the difference of quark mass. This is called a Ckm mechanism. Okay. So in fact, people guessed what the mass of strange quark is, just based on this. Charm. I don't know what I'm saying. Charm quark. Yes, just based on this effect. Yeah. Huh? Nobody believe it? Oh, okay. I don't know. Oh, I see. Okay. All right, but this is called I think, what is this? Glashow-Ilianopoulos-Mariani mechanism. Okay. So, but let me there again. Let me emphasize again that all this flavor structure is tested very, very well, and we're still keep testing it, going to even further, and there's always, if you look for anomalies, there's always some potential anomalies in this test, but none of them turns out to be there. And yeah, anyway, but it's very, very well. At least this is a very, very close to the actual story. Okay, but this is a standard model. Okay, standard model again. I will say the story is I have this flavor symmetries, and the flavor symmetry is only broken by the spurions of Yukawa coupling. Okay, so that's the standard model. On the other hand, you can also imagine there are irrelevant operators give you additional source of flavor violation. Okay, so this is a additional, additional flavor violation by irrelevant operators, right? Just like I can break a baryon lepton number by writing down additional irrelevant operators. I can also do this with flavor. So again, so for example, you can imagine there are operators like this, right? Okay. Again, I'm not very careful with the Lorentz structures and indices and so on, but there are you can write a number of operators with 4 different flavors. Okay, this is consistent with all the standard model gauge symmetries and so on. Right. Obviously, these things will contribute to observables like Ckm mixing as well. In fact, Ckm mixing is actually one of the things that give you the strongest limit on operators like this. Okay. So Ckm mixing means that M is greater than 5 order magnitude above the weak scale. So, okay, so we'll come back to this effect, these facts. Okay, these are all very important when you think about the beyond standard model new physics, right? Because these are obvious constraints. Okay. Now leptons. I talked about quarks, and I can go faster with leptons. Is this reasonable? Can you read this? Okay. I don't need to. So YE is 3 bar under left-hand rotation, right-hand rotation. Okay? Now, for the moment, let's ignore neutrino mass. At the moment, let me ignore neutrino mass. Okay? Because that's something different. Okay? So imagine neutrino has a very small mass. Imagine its effect is very small. Then this Yukawa coupling, this sporion breaks this flavor symmetry. Okay, and it's slightly different. This Yukawa coupling, so U3 square by this Yukawa coupling, it breaks down to 3 separate lepton numbers. Okay, you can do the counting that you can yeah. So there are 3 separate preserved lepton numbers: electron lepton number, muon lepton number, tau lepton number, and you can count that these rotations are enough to remove all the phases in this Yukawa coupling. Okay, all the phases in this Yukawa coupling, and there are only 3 real parameters in this case. Okay, which is the mass of those 3 guys. Okay, that these are the only yeah, these are the only physical parameters without neutrino mass. Okay, so just okay. But now we know neutrino has mass, so let's talk about neutrino mass. Okay. Yeah. What do I do with this? Okay. Well, I think that's it. So the most obvious way to do neutrino mass is just do it in the same way as the quark mass, right? So you already see the problem here. The difference between the neutrino and the quark is there's a right-handed quarks, but there's no right-hand neutrinos. Okay, I haven't added right-hand neutrinos. Why? Because I don't know whether they are there or not. Okay, right-hand neutrinos, unlike right-handed quarks, right-hand neutrinos does not have any interactions in the standard model. Does not have any standard model gauge interactions. So, in order to see it is very difficult. But nevertheless, let me just say, okay, suppose I add a right-hand neutrino. Okay, first way to have a neutrino mass is to add a right-hand neutrino. Okay. Let me call it neutrino. Let me call it N. Okay. So it's then in addition to the electron Yukawa coupling, now I can write another Yukawa coupling with the right-hand neutrino. Okay. Then the story in this case is very, very almost identical with the standard model. With the standard model quarks. Okay, so again, there are two Yukawa couplings, 3 U3 symmetries. So suppose I add 3 right-hand neutrinos. Okay, suppose I just add 3 right-hand neutrinos. Okay, then the story is literally identical. It's isomorphic to the story of quarks. And so that's fine. And but on the other hand, you may be bothered by the fact that the neutrino mass is very, very small. Okay, neutrino mass. What's neutrino mass? Used to be, I think. Yeah, it's much lower than that now. So the answer is we don't know. we have some hint. That I think it has to be less than 0.1 eV, So, but we don't know its absolute value. We know its mass difference. We know 2 mass differences and some mixing angles, but we don't quite know the overall scale of neutrino mass. There's some the 0.1 eV is from cosmology bound, from structure formation. So, but if you bother by the fact this is very, very small. You maybe we can think about the neutrino mass is actually coming from irrelevant operators. Okay, so let's do it with irrelevant operators. This is called, I think it's called a Weinberg operator or something. It's that I don't know what. Yeah, it's LH square. Okay, it's that operator. So this is a doublet, this is a doublet. You can form a singlet and just square it. Okay, and this is dimension 5, so this is 1/m. This is the lowest dimensional, one of the lowest dimensional irrelevant operator you can write for the standard model. Okay. Right. So in order to give neutrino mass, suppose that my aim is to give neutrino mass 0.1 eV. And this scale has to be about 10 to the 12 to 10 to the 13 GeV. Okay. So which is okay, reasonable. I don't. And in this case, however, it's different because you notice that the lepton number, there's no lepton number anymore. This term violates the lepton number. Okay, so in this case, the symmetry breaking is U3 squared down to nothing. Okay, lepton number is not preserving. Okay, so the one way of distinguish these two possibilities is to see whether there are lepton number violating processes. Okay, again, but because the neutrino mass is tiny, this is very difficult Okay, so one of the future targets for future experiment is to test which one is correct. Okay, so but either way, now we have flavor rotations. Flavor rotations become physical again. Okay, either way, now we have instead of Ckm, there is some other matrix called a Pmns Matrix, which is basically the combination of the left-handed rotation of neutrino and the charge lepton. Okay, it's again pretty similar to the quark sector, and they also have 3 mixing angles, 1 CP phase. Okay, in this case, and in general, well, this is much less well measured than a quark because measuring neutrino is very difficult. We have pretty good ideas of how big those 3 angles are. We don't know the size of that CP violation angle yet. Okay. Although I will be surprised if it's a 0. So let's just say we have seen it done it once in the quark sector. Seems to me that there's no reason to assume CP is a good symmetry for neutrino. Yes. Yeah. It's well, we can come back to this naturalness question later. But neutrino mass somehow bothers people much more than the rest of. I mean, for the rest of it, you can also write higher dimensional operators. There are actually papers written, by, and there are other limits on those models and so on. But this is yeah. Anyway, I think because 0.1 EV is really much smaller than the. So if you look at the, well, it's hard to see. It's hard to say which hierarchy one should really be bothered by. But anyway. By the way, sorry, neutrino is the only possibility you can actually write this operator. Okay, the other things you cannot write this operator. You can write other higher dimensional operators to give you mass. So that's also, it's a little bit harder to do it for the other other masses. Okay, so of course, just like a quark flavor violation, we can also test the lepton flavor violation. Okay, there are also lepton flavor violation measurements. So. And all this picture can also be violated by irrelevant operators. So the one set of irrelevant operators is, for example, this. Okay. So these are the L and J, and this is a doublet form, and then this is a gauge invariant. Okay. This okay? So this is it's almost the same as Yukawa coupling, except I have these guys. Okay. And also I can have operators like, for example, Li. Yeah, just A and B, and these are different flavors. I can also have these kind of operators. Okay, so these operators can be tested by, observing mu goes to E gamma. So muon usually don't decay that way. Okay, but this has to be a very rare decay mode of muon. So you can try to observe that. Also, you can observe see whether muon goes to 3E. Okay, so let's see, E plus, E minus. Right. Okay, you can try to observe that. Okay, so these things are all constrained, these parameters. Roughly speaking, this tells you that M needs to be greater than. Okay. So slightly less stringent than the K-on mixing constraint. K-on mixing is 10 to the 7 GeV. This is 10 to the 5th. Okay. Any questions about this? This is all we want to say about flavor physics. So this is a, I mean, there is mountains of literature in flavor physics, and I think this is just an overview of what. Yeah. So the bottom line is, the standard model has a very specific structure of flavor, and they have been tested very well. Okay, except perhaps there's one parameter here in the neutrino sector still needs to be determined. Okay, so any additional flavor violation effect, it has to be fairly strongly suppressed. Okay, the suppression scale is from 100 TeV to 10,000 TeV. Okay, so okay. How much time I still have? I don't know what the. Oh. Okay. Let me just tell you what I'm going to do next. Okay. So next time we'll start to begin by talking a little bit about the QCD, the theory of strong interactions, and its SU and gauge theory with vector-like quarks and so on. And what's interesting about the QCD is that there is a scale where there's a phase transition happens. Okay, so that scale, which is called lambda QCD, is about GeV. Okay, above that I have a series of quarks and gluons. And well, it's very difficult, as you learn from Len's lecture. But in principle, you can do perturbative calculation to predict observables. Okay. Around the GeV, I think only Tom knows what's going on. And below GeV, though, around 100 MeV. Okay. Then this is a series of pions. Okay, so this is around the MeV. This is a series of pions, and there you actually can do perturbation theory again. Okay, so it's called the chiral perturbation theory. Okay. So next time we will talk a little bit about the chiral perturbation theory, not because we wanted to dig into any details of our chiral perturbation theory. It's again a very deep topic, very difficult. But I wanted to. There are certain concept there is useful for later on. We're talking about the rest of the standard model and the BSM. So I will go over a little bit about the chiral perturbation theory, how to describe pions. Okay. Yeah.
What does this CP violating operator look like that comes from the phase?
Yeah. So CP violation, we can just talk about CP violation, but for example, okay, there are many CP violation operators that you can write. For example, this violates CP. Okay. And well, if I make this into quarks, then it becomes a dipole moment or type of operator that violates CP. And so standard model, yeah. So I should say that there are also very stringent tests of CP violations from the standard model and the beyond standard model. So the K-on mixing, for example, you can also test CP violation in K-on system. that also give you one of the strongest constraint on any of these CP violating operators you can add to the standard model. You can also test, for example, this kind of operator give you electric dipole moment of electrons, and you can also test that. And in standard model, it's tiny, okay, and it has to involve quarks, higher loop involve quarks, as you know. But in beyond standard model models, this can actually be quite big, and in fact, that's also another strong constraint on the type of BSM series that you can write. Okay.
Yeah, I was asking about the extra phase left over.
Yeah. Yeah. So there, if you want, there is a phase in the Ckm matrix.
Oh.
Yeah. So if you when you construct this, when you calculate these operators from the standard model, that phase will enter. And that's not a very good way of saying. A good way of saying it is you can actually construct a phase rotation invariant CP violation and out of Yukawa couplings. And you can construct invariant out of Yukawa couplings and flavor rotation invariant out of Yukawa couplings. That's CP violating. And then it really doesn't depend on whether you go to the mass space or not. And you can show that all these standard model CP violation effect is proportional to that invariant. It's called the Yaskov invariant. Right? So it has to involve 3 generations of quarks and so on. So therefore, it's suppressed by the light quark mass. So it's pretty small. So again, CP is not a good symmetry of a standard model, just like a flavor. But the violation effect is very well controlled and given by a set of sporions. Okay, now, and these are setting very stringent constraint on any BSM models. So, yeah.
So what is known about the it's neither force nor mass, but is the first order rotation?
No.
He is being poetic. That's a poetic. That's a poetic picture. What he's saying is that at higher energies or at short distances, you can treat QCD perturbatively. At long distances, of course, you cannot. Okay, and then at very long distances, they're going basically. This has nothing to do with fat and this is poetic. But it's poetry that you see all the time when you talk to physicists.
Okay. All right. So we'll have a poetic sketch of chiral perturbation theory next time.